Yeah, thank you for the introduction. So the title of this work is AST-assisted LM retrieval for cross-stage design flow parameter tuner. This work is mostly done by my student, Renji Wang, in collaboration with the Duke University team. Okay. So I won't talk too much about the motivation. Yesterday's Liang also talked about this design flow parameter tuning by changing the two parameters that will generate large impact to the PPA. Okay. Okay. So automatic flow parameter tuning is not something new because recently we have seen this work. From 10 years ago, people started to study automatic flow parameter tuning. These are some typical approaches. For example, Bayesian optimization. This is one of our early work. This is the idea is similar as the Bayesian optimization, but based on a machine learning model that is random forest and actually boost. And this one was by Andrew's team, got the MLCAT Best Paper Award last year. This is agentic AI-based flow parameter tuning work. And this one is by Duke University in collaboration with the Synopsys, published in ICCAD last year. And so this table, so look at the main features of these works. Actually. So if we look at the parameter tuning, pretty much a two-part. One is how to find the initial solution, and then how to do the tuning. Right. Okay. So how to find the initial solution for a human being, experienced designer, they will exercise their own knowledge. Okay, for this design, where's the best place to start, right? And for automatic approach, then we need to look at the HDL code and also technology profiles, right, to make a decision of initial solution. And for the tuning, there are different methods. There are two different approaches. One is to run the entire flow and then get feedback. Or we can get intermediate feedback in the middle. So that is a stage by stage. We will say that this one would be better. These just show some different approaches. Okay. 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 And so given that there have already been so many previous work, the overall strategy from our approach is not that different. We start with this retrieval-based warm start. That means we will automatically find a good initial solution from prior knowledge. Okay, and we do this tournament-based pruning. That means we concurrently evaluate multiple solutions, and we do stage by stage running. Okay. So this is the overview. Two stage. The phase one is to generate an initial solution, and the stage two is a stage by stage Bayesian optimization. The top level framework is not that different from the previous one, but the details are different. That is why how we make some difference. Okay, so these are some details how to get the initial solution and how to do stage by stage this tuning. Okay. Okay, so let's first look at knowledge-based retrieval. The key part is that we keep a design database. That is pretty much like a human being. There's knowledge saved somewhere, right? So this is by JSON file. So given a new design, RTL and the spec, how to find the initial solution from this database? We use two techniques at the same time. One is to use a large language model. We use a large language model to get the design summary. And from the design summary, we first extract the top K candidate that is closest to the given design. So there are many designs here, right? So we use large language model to get a summary and to find the top K best match. And okay, so next, actually, that is the part that make main difference That is why we call our method like Astro, that is AST part. AST is abstract syntax tree. And for those of you who are not familiar, so if you start with the HDL, you do compiling or logic synthesis. The first step is to convert the code into abstract syntax tree. So this is an internal representation of this HDL representation. Okay, so this is a key part. This is a key difference from the previous work. We extracted this as AST, and we use AST signatures to choose the closest design among the top K candidates. So that's the key difference. Okay, and the question is that how to use this AST information. We extracted some signatures. We use like 3 different signatures. 2 are from existing approaches. You see these are from other fields. Okay, so one is SimHash. SimHash is first we use some hash function to embed those AST features into some vectors, and then use the Hamming distance to tell the difference between different signatures. MinHash is another approach to look at the set overlap. So these 2 are good in a sense to get an overall similarity, but it has weakness in a sense that it neglects some details. So in order to address this limitation, we invented our own metric. There's some details. I won't talk too much in the paper. So that will capture some details from the signature. But it by itself is not good. So we use a combination of these 3 to evaluate the similarity between 2 signatures, from 2 different designs. These are some mathematics. So if you like this, you can see from our papers. Okay. So then the overall similarity is a weighted sum. Okay. Later on, I will show one advantage of this approach is that is robustness from the description, because the input for the design, that is the Verilog code, right, and also design spec, and quite often the Verilog code has some comments, right, and later I will show if without using this AST or using some other method, they're pretty sensitive to the way the code is written. So for example, if you change the module name, if you remove the comment, then the result will be different. But our approach is based on this AST that is much more robust. Again, it's these, language variations. Yeah. Okay. So based on these 2 steps, first we use large language model to get top K candidates, and then we use AST signature to get the closest design. We use that as the initial solution for the parameters for all the stages. Okay. So this is a stage-by-stage Bayesian optimization. Bayesian optimization itself is nothing new, but there's something new here is that the surrogate model. One common surrogate model for Bayesian optimization is Gaussian process, but here we use 2 different surrogate model. Besides the Gaussian process, we also use this tree-structured Parsons estimator. And this one is better to handle those discrete space. Then the question is that for each stage, we may choose different surrogate model. Then the question is that in which stage you choose which surrogate model. We let a large language model to make the decision to make the call here. Okay. Okay. So there are some others, are somewhat standard. So for each stage, we have a multiple threads of Bayesian optimization, and we do some pruning because we have some initial solution. We have the so far best solution. It's not hard to do the pruning. And for each stage, we also monitor the progress. We have some early stop mechanism. Okay. So another part, important part of this approach is that what is the objective function for the Bayesian optimization, right? So for different stages, we use a different objective function. And one reason is we found is that, for example, in logical synthesis stage, if there are some timing violation, actually it's not that critical because if there's some small timing violations, that can be fixed in the later stages, right? But at the layout stage, in the later stage, if there's a timing violation, you don't have any more chance to fix that. So we use a different objective function. I won't go through the detail here. The key part is that, so here, the timing violation is more of like a soft constraint, but at later stages, it's a hard constraint. Okay. And so after this, the run like one design, we added the result back to enhance this database. Okay. So I'll start to show the experimental result. This is the setup. We use both the Synopsys tool and the Cadence tool. And we use the 7 stages of the design. And so this page shows the test case. These are 3 previous work. Our test cases cover all these previous work. We use more cases, and we use bigger designs. So this page is the main result on RI. So power versus slack and area. Okay, so this column is from our result. So if we look at the timing part, so this is on average, we can achieve, the best, the positive versus slack, but other alternative approach, they still have a negative versus slack. And we have a smaller area and smaller power. And also runtime, we can achieve this with about half runtime because, we can run less number of time. So this one is more details on each individual cases. Okay. So this is one I'd like to show you why we use this ST-based approach and how this similarity metric matters, right? And so this is, okay, so this one shows that if we only use large language model to compare one design and the database, for the original design, that is fine. The alternate means we make some perturbation of the code. We change the module name, we remove some of the comment, then the result becomes really bad, So this means the number 1 match, the top 3 match, okay, the result is really bad. So our approach, the similarity metric has these 3 components, right? This one is good, but it is robust, but even the original one is not 100%. These 2 are not good, but if we put them together, it is good at the original design. Even we change the design name, we remove the comments, the result is still pretty good. This one is to show the effect of this warm start to exercise the knowledge of the database so that we can get better. So the score is the lower the better. For some cases, there's a big improvement by good initial solution. So here are the conclusions. So we propose a new automatic design flow parameter tuning framework. And the key part is to use ST to retrieve, the closest design. And also we have some new techniques for the tuning part. Finally, we got better result. Okay, thank you. Yeah.
So thank you very much for the talk. So we can take some questions.
Thank you. Good work. There are different ways to generate the abstract syntax tree from the same RTL that could yield very different ASTs. How robust is this to, differences in AST graphs that represent the same logical function?
Oh, you mean like a different ST representation?
Correct, yeah.
Oh, we haven't tried that. We just, we use some, I forgot which tool. We use some tool to parse the Verilog code to get ST, but we didn't try different parser, right?
Okay, thanks.
Yeah.
Hi, Professor Hu. Good talk. So I have a question about the slice 20 table. So why, I thought ST grounded after altered, why still there is a drop dropped to 100 to 95.8% after retrieval.
Which one?
In the last column. So it looks like you altered some comment in the code or something.
Yeah, so these are the original Verilog code, and these are like for the code we make some changes of module name, and also we remove some comments.
Yeah, exactly. So Astro Tune, if you look
Yeah,
at
so
the last column.
the key part is that AST is, how to say, it is a logical structure that is, has some tolerance to those name changes, you know, yeah.
Oh, you mean you changed the comment and the ST might...
That means we don't rely too much on the comments, yeah. ST itself has nothing to do with the comments, right? If you use a large language model will inherently rely a lot on comments, but the ST does not use comments.
Yeah, that's the correct thing. So I was thinking it should be, after alter, it should be still 100%.
Oh, 100%.
Or I got it wrong, the idea.
It's not perfect, I know.
Or
Yeah.
is it basically the
And
encoding
also, these
part?
two are different. This one means the top 3 try. This is only top 1 try. Then it means like, you know, we take the top 1, you know. So this is one's really hard one, you know. I would say this is already pretty good, but hopefully we can do better, you know, yeah.
Okay,
Yeah,
thanks.
yeah.